Okay, so we ended last time with talking about E. We defined E, and then we introduced the idea that E has an inverse, right? E to the x, excuse me, has an inverse, and that inverse is what we call a logarithmic function. So let's define a logarithmic function. Right? And a logarithmic function, right, is a function that is the inverse of an exponential function. And so we teased sort of at the end, we looked at a graph, and so let's see how we could compare these two things, right? So if we have an exponential function, b to the x, its inverse, right, is going to be defined as log base b of x. And if we look at the graph, right, of b to the x, and then let's separately look at the graph of log of x. So b of x, if b is greater than 1, is an increasing function with an intercept, excuse me, at 0, 1. So if you plug 0 into the exponent, 1 is going to come out. So if we look at this graph and we really kind of dig into it for a minute, we can see that there is a horizontal asymptote at y equals 0, right? So we can see the graph's never going to get to 0, but it's going to get really close. Furthermore, we can see that the domain of this function is all reals, but the range is 0 not included to infinity. So, right, because of the asymptote, it's never going to get to 0, but it will go up to positive infinity. And this would also be true if we had a decreasing exponential function, right? So a decreasing exponential function would curve down this way. It would still have an horizontal asymptote at y equals 0. The domain would still be all reals, and the range would still be 0 to infinity. A logarithmic function, right, or the inverse of this function, we know we're supposed to take the graph, reflect it over the line y equals x, and it would look like this. The intercept that was at 0, 1 is now at 1, 0 because the x and y values switch, right, when we do inverses. And instead of a horizontal asymptote, it's got a vertical asymptote. So the attributes that were associated with y on this graph will now be associated with x on this graph. So this asymptote occurs at x equals 0. This function is 1 to 1, and so we're going to get an even domain and range flip. So the domain here is not all reals anymore because it only exists from 0 to the right. So the domain is 0 to positive infinity, and the range is negative infinity to positive infinity, because we can see it's going to go all the way down to negative, and this is going to keep climbing, right? If we were to extrapolate it out, we would see it just keeps climbing up to positive infinity. So you can see here, right, this adheres to one of the properties of inverses, right? Domain and range switch, y attributes become x attributes, and vice versa. So we can use the fact that these graphs are inverses of each other to now introduce a new property of inverses. So this says if two functions are the inverse of each other, then if I compose f with its inverse, that means take the graph, or the function, excuse me, of f inverse and plug it inside of the original function f. And when you do this, x should come out. So if I take our f of x, which is b, right, to the x, And where I have x, I replace it with my inverse function, log base b of x. This works out to just be x. But we can also compose the other way. So if I take the original graph or function of x, or f of x, and I plug it into its inverse, it too will equal x. So this is the same thing, right, as saying plug f of x into f inverse. So if I take log base b, and where I originally had x, I replace it with b to the x will come out. And this is a very useful property because this now enables us to solve equations that we haven't been able to solve up to this point. So let's look at some examples of how we would solve exponential equations using logs and vice versa. So let's solve the following equation. So this entire expression is in the exponent, and I want to figure out what x is. So we want to solve for x. So the only way that I can get this x out of this exponent, right, is if I plug this exponential function into its inverse, which would be a log, right, it will just give me what was in the exponent. And so if we go back here and look at this again, right, well, if I take b to the x, and so let me write that out here for you guys. I forgot to do that. Oh, wait, sorry. I did it right here. So if I take b to the x, right, and plug it into a log, right, the log base b cancels out the base b here, and the exponent comes out, right? So that would also be true even if this were an expression. So that's what we have going on here. So we need to remember that the inverse of e to the x, right, would be log base e of x. But nobody writes log base e of x. We saw in the last class, right, that we actually would say, well, log base e is just, we call it natural log. It's just kind of a shortcut notation. So if I want to solve this expression, to get that natural log, or get that 4x minus 1 out of the exponent, I can actually take the natural log of both sides. So I'm opening a new pen here. So let's do that. And as long as I do it to both sides of the equation, right, we know it's a legal move. So I'm going to take the natural log of e to the 4x minus 1, which also means I have to take the natural log of 6. So since this is actually log base e, right, the log base e will cancel out the e in the base here, and I will simply end up with 4x minus 1. And now I just solve the equation for x like I would with any other problem. So we're going to add 1 to both sides. And notice the reason that I'm writing these parentheses here is I don't want there to be any confusion that the 1 is not inside of this log function. It's on the outside of this function. And then to get x by itself, I simply divide everything by 4. So one thing that you want to keep in mind when you're doing solving equations involving logs and exponentials is you always want to go back and verify that your solution works. So since the domain of e to the x, or e to some expression of x, is all reals, then this is totally fine. But if I had an issue, we'll see in a minute, where, you know, we always need to check and verify that this meets the domain and range restrictions if there are any. So since this domain is all reals, we're actually done and we can keep this. All right, let's look at another one. So I have e to the 2x minus 10e to the x plus 21 equals 0. So I have two expressions in here with x's in them, or two terms, I should say, with x's in them, and they're in the exponent. But the one thing that I absolutely cannot do is I cannot just say, well, let's take the natural log all the way across. That doesn't work. The natural log does not distribute across. But what I actually have going on here is I have a quadratic kind of hiding in plain sight, right? So whenever you look at an expression and you see an exponent, right, and then you see that same exponent that looks like it's doubled in another place, it's a very, very probable that you actually have a quadratic. So there's a method we can use to solve this, and it's sort of called, we can sort of set up what we like to call a dummy variable, right? So I'm going to rewrite this expression so that it looks like a traditional quadratic, because obviously you want to solve a quadratic. This could get really nasty if you try to plug it into the quadratic formula. So there's something we can do. I can say, well, I'm kind of suspicious that this might be a quadratic. So I think I've got something squared here, and this looks like the same thing by itself. So let's let u equal e to the x. So then in order to have a quadratic, well, I need to now also know what u squared would be. So if I square the left side, right, I get u squared. If I square the right side, I get e to the x quantity squared. And that means I get to multiply those two exponents together, and it does in fact equal e to the 2x. So now what I can do is I can rewrite my original expression using this u substitution. So e to the 2x is u squared minus 10u plus 21 equals 0. And now this looks like a quadratic. This looks like something I've worked with before. So let's try to factor this. So this does factor into u minus 1 and u minus 7, or excuse me, u minus 3. And I can check this. U times u is u squared. Negative 3u plus negative 7u is negative 10u. And negative 3 times negative 7 is 21. So this works. So now I'm going to set each piece equal to 0. And I'm going to get that u equals 7 and u equals 3. And this is not my final answer because I want to know what x equals, not what u equals. So now that I've gone, I can't go any further, right? I can now go back and replace u with what it was standing for, right? U is just a placeholder to get us this far. So this means e to the x equals 7 or e to the x equals 3. And if I want to get that x out of the exponent, well, I simply need to take the natural log of both sides of this equation. So the natural log of e to the x will equal the natural log of 7. And over here, the natural log of e to the x should equal the natural log of 3. Since natural log is log base e, that wipes out the e, and I get x is equal to the natural log of 7, or x is equal to the natural log of 3. So I did get two solutions, right? And they're both okay. But what if we tried to do this with another problem? All right, so let's look at another one. So what if I'd had e to the 2x minus e to the x minus 6 equals 0? Well, I still would have used my same substitution. I still would have let u be e to the x and u squared be 2x, e to the 2x, excuse me. So this would be u squared minus u minus 6. This also factors into u minus 3, u plus 2 equals 0. So then u would equal 3, or u would equal negative 2. When I replace my u with e to the x, I get e to the x equals 3, or e to the x equals negative 2. So for this expression, I can take the natural log of both sides and see that natural log of 3 equals x. But right here I have a problem. This is false because e to the x can never be a negative number. And if you go back and look at the graph, right, of an exponential, e to the x is a number bigger than 1, right? So the graph's going to look like this. And look at the range. The range is only 0, not included, to positive infinity. So there is no way e to the x can equal -2 because it's not in the range of the function. So we would actually throw out this solution, and this quadratic would only have one solution. All right, so let's look at another one. Let's find all the solutions of natural log of x squared equals 5. So there are, if we looked at this guy, the only way I can get the x out of the natural log, right, is, well, I need to plug it into its inverse. And the inverse of a natural log is e to the x. So we would plug it in, right, by raising it over e. So I would plug the original expression into e to the x, which also means I need to plug 5 into e to the x. The e takes out the natural log, and so now I get x squared equals e to the 5. Remember, e is a constant, so when I take the square root of both sides, I get plus or minus the square root of e to the 5. So technically this is okay, this is a correct answer, but this is a time when fractional exponents would actually be more useful. So another way we could simplify this or write it is, well, this is the same thing as saying e to the 1/2, right? So I could say, well, this is plus or minus e to the 5/2. So it's e to the 5th, all raised to the 1/2, and so I would get plus or minus e to the 5/2. Now if we go back and look at the original equation, right, the domain of natural log is 0 to positive infinity. So why do I get to keep both solutions? Well, you should always go back and look at the original equation. Because this x is squared, it's actually okay if I plug in a negative value because it will immediately get squared and become positive. So the domain of this side of the expression, right, this term right here will accept all real numbers except for 0. You can never plug 0 into a log. So these are non-zero, so we do in fact get two solutions. So let's look at finding domain. So we have an expression 1 minus e to the 3x minus 9. So the 3x minus 9 is actually in the exponent. And I want to find the domain of this function. So the rules are, right, no zeros in the denominator. We don't have any denominators here. We can't have negatives, right, under even roots. And no negatives inside logs. So there are no logs, there are no denominators here. The only thing I need to check is verify that we never get a negative expression under here. So I'm going to take the entire expression and I'm going to set it greater than or equal to 0. And I get to say greater than or equal to 0 because it's okay if the numerator is 0. So now I need to solve this for x. So since this guy's negative, I'm going to simply add it to both sides. So 1 is greater than or equal to e to the 3x minus 9. The only way to get that x out of the exponent is to take the natural log of both sides. So the natural log of 1 has to be greater than the natural log of 3x minus 9. So the natural log of 1 is going to be 0. And that's because this is really log base e of 1, right, equals some unknown number. and let's just say for a second that it's a, we don't know what it is. Well, I can always write a log, right, as an exponential. So this is saying e to the what equals 1. Well, there's only one number you can plug into an exponent where 1 is always guaranteed to come out. So a has to be 0. So log base anything of 1 is 0 because it's basically saying e to the what, right, equals, it's basically going to say e to the a equals 1, and that only thing a can be is 0. So that means on the left side here I have 0. On the right side, the natural log took away the e, so I get 3x minus 9. So then I keep solving the inequality. 9 is this negative 9. I'm going to add it to both sides. And then I'm going to divide both sides by 3. So this says that any x value less than or equal to 3 will work. So let's draw our number line. Here's 3. 3 gets to stay because of the equal to sign. X is less than that number, so I'm going to shade all the values to the left. And now I can say that the domain of this function is negative infinity to 3 included. So we can also use this property of inverses to solve an expression that we weren't able to solve before. So I gave you, we played a little game with exponents a couple of sections ago where I gave you 27 raised to some stuff equals 81 raised to some different stuff, and we sort of found 3's hidden inside of both sides of the equation. Well, now we can use the algebraic property that says if you have the natural log of anything raised to an exponent, that is equivalent to saying I'm allowed to move the exponent out front and say it's the exponent times the natural log of that value. This is true for log of any base. So log base b of a to the n would equal n times log base b of a. So we can use that to solve an expression like the following. So what if I have 2 to the x and it equals 5 to the 4x plus 3? So the first thing we want to check for is, do we have a common base here? Because it would be really great if I could use that awesome algebraic property, right? But 2 is prime, 5 is prime. There's no way we can rewrite this. But since I know that logs allow me to move exponents down to the front, right? In order to solve for x, I got to get these guys out of these exponents. Well, I can simply just take the log of both sides, the natural log. I can actually do log base anything I want, okay? So usually we like to do natural log because it's just easier to write and we don't have to write the base. So I'm going to take the natural log of both sides of this equation. So on the left side, this property says, well, I can move the x out front. So I'm going to get x times, right, the natural log of 2. And on the right side, I'm also allowed to move the exponent out front. You have to use parentheses here because I need to make sure that this entire expression gets multiplied times the natural log of 5 because I'm going to have to distribute. So in order to solve this for x, I need to get all the x's on one side of the equation, but this x right here is trapped inside these parentheses. So the only way I can separate it is if I distribute out the right side. So we're going to leave the left alone for a minute. And on the right, I'm going to have 4x times the natural log of 5 plus 3 times the natural log of 5. Now I can get every expression with an x and move it over to the other side. So x natural log of 2 minus 4x natural log of 5 will equal 3 natural log of 5. I can factor the x out on the left. And then to get x by itself, I'm simply going to divide the right side of the equation by all of this stuff in the parentheses. So this is the exact answer. So now we actually have a tool where we can solve an expression using exponentials, right, with different bases where we can't always find like a b to the m, b to the n situation. So there's actually a lot of cool properties that logs have. So let's take a look at those. So the first thing we just got to peek at, right, says, well, log base b of 1 equals 0. Oops. So b is just got to be a base greater than 0. And this is true, right, because we can always write this as an exponential because b to the 0 equals 1. So that's why this guy is true, right? We can also say that log base b of b is 1, and that's because b to the 1 equals b, right? We can always say that's the base, right? And then you flip the order of those two numbers when you plug it in. We also said, well, if I plug a log into its own inverse and vice versa, that works. So that means, right, b raised to the log base e of x equaled x. So this base and this base have to match, right, in order for this to be true. Similarly, log base b of b to the x equals x. So once again, the base of the log and the base of the exponential have to match in order for this property to hold. Furthermore, we can say, well, if I have log base b of m divided by n, and this could be a number or this could actually be an expression, then this is the same thing is saying log base b of m minus log base b of n. So there may be reasons that I want to combine these into a single expression, but there are other reasons that it might be advantageous to spread them out. So just like with our exponential rules, you want to make sure you know these backwards and forwards. Log base b of m times n, we can separate it by saying log base b of m plus log base b of n. So a division sign translates into a minus, a multiplication translates into a plus. And then we just used in our last problem log base b of anything raised to an exponent. We're allowed to pull the exponent out front like so. So these rules hold for any base, okay? But there are, if you ever look on a calculator, you'll notice that you have a log button and you have a natural log button, right? So natural log, we covered, is log base e. So you're expected to know that. So if you wanted to raise this over its own base, you would raise it over e. But if you ever just see log, right, with no base written right here, it is implied that this is log base 10 of x. So if you ever work with, in chemistry, you might look at the pH scale. The pH is a log scale. It's log base 10. The Richter scale how we measure earthquakes is a log scale. It's log base 10. So if there's no base at all written, it's implied that it's a 10. Kind of like if it's a square root, we don't write the 2 out front. It's always implied that it's a square root. So let's use some of these properties and simplify some log expressions. So I want to simplify log base 2 of 16. So I actually want to know what this equals. So you don't have a log base 2 in your calculator, so you can't even use a calculator to do this. But in the same way that we said, well, if I look at the base, if I can find some 2's inside of here, then I know that when you have the log, right, of something with its own base, the exponent comes out. So the question is, how do I rewrite 16 in terms of 2? So log base 2, right, 16 is the same thing as saying 2 to the 4th. So now I have log base 2 of 2 raised to the 4th. So the log base 2 of 2 will cancel, and I just get out 4. So this is an example of an expression being plugged into its own inverse. So the exponent comes out. So if this were an x, we would have said x, right? If this were a 5, we would have said 5. But we just need to make sure that the bases match. All right, let's look at another one. So log base 3 of 1. Well, this property right here says log base anything of 1 is going to be 0. So the answer here is just 0. So log of 0.1, okay? Well, log without any base written means base 10. So I have to figure out, can I find some 10s inside of here? So 0.1 is 1/10. So I can rewrite that as a fraction of 1/10. I can't cancel it because I need it to be 10 raised to something. But I know from my properties of exponents that 1/10 is 10 to the negative 1. So now I have log base 10 of 10, and this expression simplifies to negative 1. So log base 2 of the square root of 2. So the base is 2, so we have to find some 2's in here. Fortunately, I see one, right? But I need it to be 2 raised to a power. So the square root of 2 can be written as 2 to the 1/2. So now log base 2 of 2 cancels, and my final answer is 1/2. So now I have the natural log of 1 over e squared. So kind of like what we had over here, right? The base of natural log is e, but I need to rewrite this to be e raised to a power. So I'm allowed to move it from the denominator to the numerator as long as I multiply the exponent by negative 1. So natural log will wipe out the e, and I just get negative 2. So the base can be a fraction, right? The base just has to be positive. So now I have base 1/2. So now I got to find some 1/2s in here. So before I can find a 1/2, I just better start out probably with finding some 2's. So let's rewrite 8 in terms of 2. So 8 is 2 cubed. I can't cancel anything yet because I need it to be 1/2. So just like we did in this example and this example, right, we could move something from the denominator to the numerator. I'm also allowed to move that 2 into the denominator. So that's 1/2, right, to the negative 3. But I need 1/2 all raised to the negative 3. So this is log base 1/2. I can say, because 1 raised to anything is itself, so I can actually move the negative 3 on the outside. So now the 1/2, right, log base 1/2 cancels 1/2, and this simplifies to negative 3. So this should be enough to get you through your ALEKS homework, section 3.1 to 3.3. If you need an extension over the weekend, I'll be periodically checking my email, and I would definitely take advantage of the weekend to get all caught up, and we will dive further into 3.4 when I come back. See you Wednesday.